Hello, hello. Howdy. Oh, I'm glad to hear it. It's putting you in a calm, serene mood. That is always the goal. Okay, so we'll obviously formally kick off in a second, but I feel like there is a big bluish, greenish elephant in the room that we have to address, which is of course the hair. And I am looking. So obviously I am colorblind, but I'm looking at the camera and it does not look, I'm looking at the video stream that I'm getting, and it does not actually look like the color that I see it like over in the mirror. Some folks have joined me on Instagram and they saw the process, and I think it looked bluer on Instagram. But I appreciate the positive feedback. I did, of course, try to go blue, and I think it does look fairly blue in person. I think I do need to mess with sort of like the white balance settings on my camera. But people who can see colors around me, they are telling me that it is blue. Hey, Aerosol Can, welcome, welcome. Oh, it's so good to see everybody back, everybody joining again. That is always so lovely. Oh yes, somebody asked what my Instagram is, and actually I dyed my hair later yesterday, and so all of that should still be on my story. It is, well, Instagram is at WLifford, if you want to go find me for all the hair dyeing content you could possibly want. But yeah, no, I did not do my nails blue. My nails are still regular nail color, I guess. Yeah, long time no see. Welcome back. I'm so thrilled to have folks come back for the final session here because we are going to have a good time. So I guess without further ado, okay. Now, folks, tell me to put on the crown and I'll put on the crown. I'm never not down for a flower crown. Does that rhyme? Never not down for a flower crown. That's good. But yeah, I guess without further ado, I will really quickly pop back in and look at questions from yesterday. Oh, also, actually, I have a big request of everyone. So we are here kind of at session 4 of 4. Oh, thank you. We're here at session 4 of 4, and one of my big questions for y'all that have stuck through is on the pacing of the whole week, right? And so obviously you'll get a taste of what we're doing today, but this is always a big question that I have when I'm putting together what I do for Global Hack Week. Is I want it to be sort of accessible for entry-level folks, and I also, for folks, I mean, there are some folks who we've done this like 3 or 4 times now, kind of Global Hack Week after Global Hack Week, and trying to hit that sweet spot of it still is accessible for beginners, but also has something interesting for folks that have done this, several times with me. That is something that I'm looking for feedback on. So I'm actually just going to add a question and to the poll, and it's going to be something like was this ML track too fast? Or I'll say way too fast, a little too fast, just about right, a little too slow, and way too slow. And so that's kind of like a 5-point scale. And just let me know where you're sitting, given that you've been here, through the entire week, because it's y'all's opinion that I care about kind of the most here. Obviously, there are some issues with folks that maybe it was too fast and so they dropped off, and we'll have to deal with that. But on that note, I'm going to send out that poll one last time for y'all, and actually, please fill out that form and just answer that question: was it way too fast, way too slow, a little too fast, a little too slow, just about right? Oh, you found my TED Talk. Oh, I'm so glad you enjoyed that. Yeah, that was, I guess I'll give a quick blurb of context. In undergrad, one of my big projects, my senior thesis, it was on natural language processing, and it was on the idea of trying to identify moral sentiment in text. I think I actually maybe mentioned this on the first day, and I think that and so then I ended up giving a TED Talk on this and on the idea of, can you get machine learning models to sort of identify and learn from human morality? And it's very philosophical, it's very heady, but I ended up giving a TED Talk on it, and that is on the internet, and you can find that. But yeah, I appreciate the feedback. Who thinks this is way too slow? Yeah, I think that we've been moving pretty dang fast. I think we covered We covered like all of Python or most of Python in the first day, 30 years of linguistics in the second day, and then probably another good 10 years of machine learning in the third day. And we're going to basically come up to sort of the modern day state-of-the-art models today, or come close to it. So yeah, if you found it way too slow, I would like to talk to you. Let's chat because dang. But yeah, so this is our fourth day of our machine learning track, and we get to sort of recap and talk about everything that we've learned this week, and also dive a little bit deeper on some very powerful models. And importantly, we're going to learn about one of the biggest pitfalls of machine learning, which is called overfitting. I won't bury the lead any longer. We're going to cover overfitting. We'll look a lot of tools at how to fix this really big problem that pops up when machine learning scientists build models. Welcome, welcome, welcome. Okay, incredible. Maybe we'll pop back through those slides because it's just what we do now. And I just love the joke about how I do have slides, that I just use the same 3 slides like all the time. But I think it's nice to sort of, center us and give us a fun little consistent intro. Okay, here we are. Everybody, welcome back to the Global Hack Week in it 2022 or 2023, depending on how you count, the machine learning track, where we are taking a deep dive into natural language processing. I'll give my same blurb about this. So natural language is just what machine learning scientists call regular people talking and writing. Oh, and somebody asked for the check-in link, which is always a great reminder. And I am going to drop that link before I continue talking because it is so important to check in. Where is the announcement that I just made? Oh, there we go. I will. Thank you all so much. There's the check-in link. Please check in, make your voice heard, say that you were here. Okay, so natural language. Natural language is just what machine learning scientists call regular people talking, right? I am talking right now and generating natural language. If you are writing a text or a message in chat right now, you are generating natural language. And the reason that we care about having special tools for dealing with natural language is just because there's so much data out there, right? We're going to really look at the idea that more data can give you a better model today. We're going to take a really deep dive into that. And there's just basically a ton of natural language data out there. The entire internet practically is natural language data. And that's why we're diving into natural language this time. I'm sure that if you were here at the 4th session, you have already seen my face at least once this week. But my name is Will. I'm a software engineer at Google. I'm a coach at Major League Hacking. I am a Python enthusiast. And today, the slide says unbelievably caffeinated, which is normally a good bet. But today I'm actually moderately caffeinated. I have had 2 cups of coffee and we're at a good place. So I am moderately caffeinated today. You can find me on the internet at W Liffert. Actually, on my Insta right now, you can see the progress pics of this hair getting dyed. This is kind of our big recap. On the first day, we did a sort of reintroduction to Python. On the second day, we looked at natural language basics and rule-based models, and we introduced this idea of sentiment analysis. Yesterday, we looked at Relu's logistic regression. We actually did not get to touch on artificial neural networks, so I'm going to ask you all actually how you want this day to go. And then today, hopefully we will kind of finally get into sequence models, which are some of the more powerful models that sort of state-of-the-art machine learning engineers are using today. Okay, there we go. There are our 4 slides. And now we can hop into doing some fun stuff. Okay, so this is actually something that I want to get a rough poll on. So yesterday, we started using scikit-learn and we built this logistic regression model. And if I recall, we ended up getting like 77% accuracy, right? And that was pretty dang good. We talked about potentially getting into artificial neural networks with scikit-learn. Now, my original plan for today was to jump ahead to this library called Keras that is a part of Tensorflow, and it is kind of a little bit more nuts and bolts, kind of more intense way of building models, but you can build really, really cool models. And so I'm going to give y'all the option. Give me some feedback. Do you want to sort of continue what we were doing yesterday and continue using scikit-learn? Or do we want to jump ahead to getting our hands dirty with TensorFlow and Keras, which are kind of the I don't want to say like the more grown-up models, but it is sort of a little bit more work, and you can get sort of more powerful models there. So let me know in the comments if you want to kind of circle back around and do what we were doing yesterday, or if you really want to just kind of jump ahead and get our hands dirty with TensorFlow and Keras. We know what TensorFlow is about. What is Keras? Okay, yeah, this is actually a great question. And our 2 comments are, hey, let's jump right ahead. And I have no problem at all with that. Yeah, okay, more folks voting. Oh, Brittany, hi. And Stuart says TensorFlow and Keras. And Aerosol Can says, let's make big boy models. Okay, we do have a vote from continue from yesterday. So here's what I'll do, is I will do a quick recap of what we did yesterday, because it really sets us up for what we're doing today. So everybody can kind of have everything they want, hopefully. We'll see. Okay, so yesterday, let's see if I still have the runtime up. Yes, it looks like... Oh, you know, y'all, you'd think that I would really have all of my tabs organized at this point. Somebody said, what would you like to suggest? Yeah, I do think that I think there are some cool things that we should take a look at with TensorFlow and Keras, but I do think just rerunning through where we landed yesterday could be really helpful. Okay, here we go. Let's jump to the punch in. So this is what we were looking at yesterday. We'll do just like a quick rerun through what all this meant and why we were doing it. So we imported our data. And on the second day, we looked at sort of us manually picking some words that we thought were either positive or negative, right? We picked the words like good and love, and we picked the words bad and hate to represent positive and negative, right? And so we gave them weights of +1 and -1. But that ultimately, the issue is that we have to come up with all the words, right? And we want to actually learn from our data. That is the core of machine learning, is let your data tell you what your weights should be. And so we copied some code from the previous day. We copied some of our pre-processed scripts. And we started doing this where we said, okay, what words appear in 5-star reviews but don't appear in 1-star reviews, or don't appear in the other ones? And alternatively, what words appear in 1-star reviews and don't appear in other reviews. And we got these lists that are a little bit bigger. Hopefully you can read that. You know, words like highly and great and love. And there are some weird ones in there like dog and like weight. But we used these, and we did sort of running it through our same earlier prediction process, and we got a much better result than previously. We got better than 50%. Somebody asked, can I update this on GitHub? And absolutely. Let's say this is what we'll call this part 3 machine learning and logistic regression. That's what we'll call it. And we will, this is actually very fun, is you can just save a copy in GitHub. And we will go to our GitHub. And this is actually a great point, is you can hop over to the GitHub, which I will drop a link to. Oh, hello, Hannah. It's so good to see you. Welcome, welcome. And so you can see all the code we wrote yesterday, and I will also share a link to the code we write today, so you can follow along sort of live. Oh, thank you. Thank you for the compliment on the hair and the flower crown. Yeah, I think it turned out okay. I'm pretty pleased with it. Okay, so sort of finishing our run through. Yeah, it did come out a little bit greener than I expected, but part of this, I have to promise to you, is this camera and the white balance on it. When I was taking pictures for Insta, it looked a little bit more blue. But so just by learning our positive and negative weighted words from our text, we jumped up to 52% accuracy, right? Then we learned about this idea of vectorization, where you can turn your words into numbers. And the reason that we needed to do this is because all the most powerful models out there, they all use an input of vectors on their input. And so turning our words into numbers lets us take advantage of all these sort of pre-made powerful models. And so we looked at this example of vectorization in a very simple case where we only had a few words. But then we jumped into using these tools from the library scikit-learn. They have a pre-built count vectorizer that did the exact same thing for us. And then we threw it into logistic regression. And we grabbed logistic regression because it's a model that we basically have already implemented, right? We looked at the data and we established some of these words should have positive weights and some of them should have negative weights, and then compared those weights to a threshold. And that's what logistic regression is. And I'm gonna come clean here and say that logistic regression actually is a really, really good model to apply to sentiment analysis. And one of the reasons it does work relatively well is just because of what we're talking about, the intuition of some words are positive and some words are less positive, right? And so that is one of the reasons that we're able to get relatively good accuracy. We got 77% accuracy. And so that's basically where we left off. All of that code is now live on the GitHub. I think I posted the GitHub link already, but here is the link directly to the notebook from yesterday. Taking a look back at our comments, the fact that the video name thingy matches the t-shirt and hair color. Oh yeah, that's fun. My little name tag matches there. Cute. Hannah says it's reminding her too much of linear algebra class. Yes, yeah. I mean, this is always a balance of some people want all the math and some people are like, just explain the concepts. And so we are balancing the math and the concepts, hopefully. But, you know, as always, let me know. Give me feedback on whether or not you want more or less math. I just saw that some folks have already sent in their responses on how fast this course has been. It looks like some folks are thinking it was a little bit fast, but a lot of folks think it was at a just right speed. And so that's actually really, really helpful feedback. So if you want to weigh in, please let me know. Luna, thank you for tuning in. It is good to see you again. Yeah, I mean, this is where we ended up. The camera makes it look a little bit greener than it actually is. But yeah, I guess without further ado, we'll jump into our goods for today. And let's, per usual, jump into Colab, and we will do a new notebook. And to start off, we will just copy over our code for importing our data, because that is what we're going to do first. And I just need to find my old. Okay, perfect. Yes. Okay, so this is the chunk of code that I'm going to copy over. And like yesterday, I will actually share this notebook live. So we'll say anyone with the link can be a viewer. So if you want to follow along just sort of live with all the code I'm writing, this is your way to do it. And let me know if you're having trouble accessing that link. Yeah, hi, Adam. Welcome. Oh, thank you. Yeah, in the background, it's a little bit messy. My friend is coming to stay with me before we climb a mountain, and so the little portable mattress is over there, but the fish are over there. And actually, before we get too deep, somebody a couple days ago asked in the form if they could see the fish. And so I will actually take a quick break and let y'all see the fish, and I'll zoom in on them. My Mac background. Oh yeah, well thank you for that as well, I guess. Okay, let's see. We'll rotate this over and we will see if we can zoom in close enough to see some fish. Oh, you really can't, can you? Okay, hold on just 1 second. I'm gonna grab my zoom lens and see if that gets us close enough. What? Boom. Warning, things are going to look really weird for a second, but they will go back to looking normal, hopefully. Don't try this at home. Alrighty. Now let's get back on the zoom lens. And let's see. Oh, okay. And let's zoom in. Oh, it's actually going to work. Oh, yeah. Thank you for the reminder to jump to full screen because I forget to do that all the time. Okay, we're hitting up against my monitor because the camera's behind the monitor, so I'll zoom out just a little bit. Actually, there were the fish right there. I don't know if you can see Harold. Harold is hiding somewhere. But yes, the fish. Oh, can I get in the? Oh my gosh, the fish are tiny. That was a little bit too much of a close-up. Okay. On that note, I think we're gonna pull it back. But somebody asked, and this is what I'm saying is fill out the. Yeah, I know it's a little too much for me personally, but also I don't want to take the time to change back the lens, so we're just gonna go with this. Oh, the names. The names are okay. I'm actually gonna the fish cam I don't have set up, but I will jump over there. Wait, where is the? Yeah, okay. So you can see the fish cam actually isn't set up, but the fish's names are Blahaj, Piefish, and Luffy, and those are their names. They are neon blue tetra, is what they are. Yeah, and I like them a lot. Yeah, the fish are more blue than my hair. You know, I tried. This is what we got. But we're burning daylight. We're burning daylight. Let's get back to the content. Boom. Okay. So this is how we're just going to import and we're going to start off with 10,000 records. And 10,000 records is, I would say, like a good amount of data to kind of play around with. But we're going to be testing things out, and later we will add sort of all the data in there as promised. Yeah. Oh yeah, Brittany, you named Piefish, didn't you? I think that was the name that you picked. I might be misremembering that, but yeah. Is anybody who named? I forget who named Luffy and Blahaj. Actually, Adam named Blahaj. What am I talking about? Yeah, we have the fish's godparents here. That's really powerful. Okay, cool. So we have imported our data, and that's looking good for us. And we are going to jump in and start using Keras. So there are a couple ways of explaining what Keras is. And really to do that, we should back up and talk about Tensorflow. So Tensorflow is a really, at its core, it is a, we're back to my face being really big. It is a library to perform matrix operations. And so if you have taken any classes that had matrices in them, right, it's like these big grids of numbers. And in Python, we really refer to matrices as arrays. But TensorFlow is really, really good at chaining together different operations. And we talked about this a little bit yesterday. But when we're doing some of these bigger models, even like logistic regression, really all of them can be reduced to these really big math operations with lots of numbers, right? And so this library that's really good at chaining together these math operations allow you to build really complex models. And that's really where TensorFlow differs from scikit-learn, is scikit-learn will give you sort of pre-composed models, and they'll say, hey, here's a whole logistic regression model for you, or here's a whole multi-layer perceptron neural network model for you, right? Which is what we were going to do if we had more time yesterday, but we're kind of jumping ahead. And they give you sort of in a nice little package. And that is really nice because you don't have to do a lot of setup work. But TensorFlow gives you the option to really get in the weeds and tweak little details and make a model that works really, really well for you. So for example, we did sentiment analysis yesterday, and we're going to be doing sentiment analysis today again as well. But you also have the power to do things like generate text, right? I'm sure, actually, it's wild we haven't talked about this. I don't know if anybody saw the headlines about this model, this chatbot model at Google called Lambda that one of the engineers thought was sentient. Yes, yeah, this is the one. And I'll say I have talked to this model. It actually had really, really interesting things to say about gay music. I asked it if it likes gay music, and it had the nuance to say, well, what do you mean by that? Do you mean music that is written by a person who is gay, or do you mean music written by somebody who is considered a gay icon and listened to by gay music, even though they themselves are not gay? And I thought that was just like a really, really great nuanced parsing of what it meant to be gay music, quote unquote, right? And so I thought it was really, really fun to talk to. I do not think it is sentient in any special way, but we can talk about that more in the future. Let's see. Wait, OMG, how did you figure out the big screen with the camera without the StreamYard background? Oh, Hannah, yes, I did figure it out. You have to go under settings, under, I think it's under layouts, and there's just a click box to get rid of the crop. Yes, I mean, so we could, y'all, I really am going to try to not turn this into philosophy hour, but I personally believe that that consciousness is a thing that that really is going to attach itself to any kind of physical matter, right? And that we have maybe a special kind of that property because our brains work in certain ways. But that there's no reason to believe that if I'm made out of physical stuff and I experience instant consciousness, that like a rock is also made out of physical stuff, then it maybe doesn't have like a little bit of consciousness, right? And maybe you can make a case that photons have zero consciousness just because like the whole speed of light thing. But so that's where I get to my, well, does it have consciousness in any kind of special way conclusion? And I think, at least for that model, the answer is no. But the point is that it was built with the tools like TensorFlow that are really capable of getting in the weeds and tweaking things yourself. And I will try to pull it back from philosophy hour and get back to machine learning, which is what we're here to do. But yes, I did talk about it. I won't say that I could do anything because there are certain things that if I did, I would probably get fired, you know. But yeah, so that's TensorFlow. Now, pulling back a little bit, we're going to be using a sort of a submodule of TensorFlow called Keras, Keras. I guess I'll type that out for you. And what Keras does is it removes a little bit of the work that you have to do. So there's a good comparison to PyTorch. TensorFlow and PyTorch are two of like the big libraries out there. They're both you can use both of them in Python. But what Keras really does is it makes the world of TensorFlow a little bit simpler. And so instead of having to do all of, kind of knowing what matrix math you're doing, it gives you these nice abstractions over it that we call Keras Layers. And so in TensorFlow, you have this idea of these sort of direct hardware tensors that are just numbers, getting multiplied. And Keras has these slightly more user-friendly layers that sort of abstract away some of the cold, hard math. And so we can jump in right now and take a look at sort of a very basic Keras model. So let's say we're going to import the Keras Tokenizer. Because that is just an easy way to get started. We'll say from TensorFlow. So remember, Keras is a part of TensorFlow. And then we'll say Keras preprocessing, because tokenization is a preprocessing step. And then it's inside the text module. Under preprocessing, we will import the tokenizer. And so remember, from the past 2 days, we've been talking about tokenizing is just breaking your text up into individual words, right? Another important thing we're going to want to do is pick a vocab size. So this is a thing that you'll do in a lot of machine learning contexts, where if you make your vocab sort of infinitely large, then that will slow down your model a lot. And we were talking about this actually the other day about what's the running time complexity. And one of the things that we said is if you can pick a constant and cap your input at that size, then you can basically ignore it in terms of running time complexity, because it's not going to scale to be arbitrarily large. And so that's what we're going to do here. So we'll say vocab size. And a very common vocab size that you'll see is 10,000. 10,000 seems to work pretty well for a lot of different kinds of applications. But you can play around with this, and we might even do that. We might say, can we make this a little bit bigger, a little bit smaller? But so now we'll actually create a Keras tokenizer, and we'll say our tokenizer is equal to that tokenizer class. And we'll initialize it with this argument numWords, and we'll pass in the vocab size. And so all this is doing is saying tokenize, but only keep the 10,000 most common words in our vocabulary. Let's see. Somebody said I've heard there's also something called TPU, Tensor Processing Unit, probably hardware like GPU. Yeah, okay. This is actually y'all know how much I love falling down rabbit holes. So yes, this is. I guess we'll back up a little bit, and we can actually talk about the history of AI and machine learning for a second. Also, tell me if I'm going down rabbit holes too much, but I think they're a lot of fun. So it really was back in the sort of late 70s and 80s that machine learning and AI became really intense subjects of study, right? And people were building a lot of models, and really actually in the beginning, a lot of the models we use today, like the artificial neural network, was a thing like 30 years ago, right? But we ran up into this problem where we realized, okay, you can make an artificial neural network with maybe a layer or two, and you can get some good results. But if you make it much bigger, and you try to basically give your artificial neural network a bigger brain, we just don't have computers that can run it, right? And a really interesting thing happened because all it was doing a bunch of matrix math really quickly, and our computers weren't scaled up to do that, right? And this really interesting historical development happened where we built GPUs really originally for gaming. That was like the original sort of the reason we started scaling our production of GPUs is because a lot of gamers wanted better graphics, right? And when you're rendering graphics, all you have to do is you have to do a bunch of matrix multiplication. That's how you render graphics. And so we built these specialized hardware units called GPUs, or graphical processing units. And it was, I mean, people disagree about when this was, but it was after the turn of the century, kind of in the 2000s, that some machine learning scientists realized, wait a second, we can use GPUs to do machine learning. Like, this is actually an application that lines up really, really well. Yeah, no, I mean, this is why I'm so glad you joined the stream, Russell, Ken, because you get me off on really, really fun tangents. And so there's a thing that we refer to as the Great AI Winter, which was the time after the original interest in machine learning, and then before the GPU became widely accessible and used for machine learning. And you have a period of 15, by some accounts, 20 years, where there really was not a lot of excitement or energy behind machine learning. Yeah, exactly. GPUs were a perfect application, and we realized all we had to do to get a lot of cool results was just make our models bigger, right? That's the thing we actually will look at today, is making your model bigger and being able to run through more data faster, and a GPU helps us do that. Now, fast forward a little bit, and I mean, the really short answer is the GPU really was made for gaming, and we realized it could be used for machine learning as well. I don't know when the TPU first came out, but in the recent years, Google, the company that I work for, so disclaimer, I may be biased or whatever, be a critical listener, they realized that they were doing a lot of machine learning, and the GPUs were good, but they could actually make a slightly more optimal piece of hardware if all you're doing is running machine learning models. And so they came up with something called the TPU, or the Tensor Processing Unit. I guess I'll jump back to my face because we're just chatting. And the tensor processing unit is really, really optimized for doing tensor operations. And a tensor, honestly, is basically just a matrix. And so the terminology here is a little bit fuzzy. But the long and the short of it is that a TPU is really, really well optimized for running machine learning models really fast. And this actually gets me into one really fun reason that I like using Colab, is because you can jump into your environment. And I would say I actually pay $9 a month to have a Colab Pro space, but I think you can actually do this even without it. But you can go to where do you want to manage sessions? No. Oh, it's right under here. Oh, there we go. Change runtime type. And so I can pick if I want to accelerate the hardware. And so I can either pick a GPU or a TPU. So I'll pick a TPU. And then the runtime shape, we'll say high RAM. You might not have all these same options. Okay, I have too many sessions that are live, so I'll have to kill some other ones, I guess. Manage sessions. And we will kill part 3 because we don't need it. And I think we actually don't need part 3 anymore either. Boom. Okay, so maybe now we can use a TPU. Like I said, Google will give you a lot of resources for free, but at some point they do start checking. Somebody asked, is the neural engine and Apple stuff kind of like that as well? Yes, this is a great point of comparison, is that some of these large tech companies are kind of doing the same thing, where they're making some very specialized hardware because running machine learning models has become such an important part of your workflow of what a computer is. Okay, so hopefully that was a satisfying rabbit hole. But yes, GPUs and TPUs are things that can make our models run faster. And we'll reconnect here. Oh no, still too many active sessions? Okay, I guess we'll have to terminate this other one. We're on Untitled Part 4. Okay. Boom. Okay, maybe now we can reconnect. So you can have several sessions open at once, but you can't have several high-powered sessions open at once, I guess is the catch. So where do we run this? We have made our tokenizer, right? And similar to what we did yesterday is before we use our tokenizer, we have to fit it on our text because we need to know what kinds of words are we going to actually see. And actually, before we do that, let's make a test and a train split. Okay, so we imported our data using 10,000, and we will create a test train split. And actually for this, we will go back and we'll use some code from the scikit-learn library. So we'll say from sklearn model selection import train test split. And this line of code is a little bit bulky, and so honestly, just copy it after I write it if you want. But so we're going to generate a train test split. And remember, this is what we were talking about yesterday, where if your teacher gives you a study guide, but then the test is the same as the study guide, you can just memorize the questions, and you don't actually have to learn anything. But if, on the other hand, you get 90 questions on the study guide and 10 questions that are separate for the test, then that forces you to actually kind of learn. And so that's what we do with machine learning models, is we split out a study guide and a test. And so what I will do is we'll say xtrain, which is like our study guide, or like the questions for our study guide, and xtest is like the questions for our test. And then ytrain is like the answers for our study guide, and ytest is like the answers for our actual test. And we'll use this function train test split. And we will throw in, we'll say our df, the text field, because that's, remember, the actual text of the review. And then we'll also throw in the score field, which is how many stars did it get. Hopefully all that should be, none of that should be surprising or new. And so we can run that, and we have both a train set and a test set. Any questions on that, on the breaking out a train set and a test set? Everything feeling good? Okay, right on. Okay, so now that we have our train set and our test set, and I guess actually just to be clear, we'll say xtrain 0. This is literally just a piece of text, right? And if we do ytrain 0, so we say I have bought several Vitality canned dog food, so this is a review. And if we do the first thing in ytrain, that's the number of stars it got, right? So that was a 5-star review. That's all our train set and our test set are. Okay, so now we have our tokenizer, and we can run tokenizer dot fit on text, and we'll pass in xtrain. So remember, this means that we're going to only consider words that are present in our training set, and if there's a word in our test set that we never saw before, we're just going to throw it out. We're not actually going to be able to do anything with it, which makes sense because if we've never seen that word before, our model has no chance of knowing what it actually means, right? Okay, so we have our tokenizer. We're going to fit it on our texts. And then what we're going to do is we're going to encode our actual text. So we'll say xtrain encoded is equal to the tokenizer, and we'll run texts to sequences. And we'll pass in xtrain. And then we actually know we want to do the exact same thing for our test set. And so we'll say xtest encoded is equal to xtest, or text the sequences of xtest. And just to be super clear about what's happening here, we can grab the first line of xtrain, and then we'll print the first line of xtrain encoded. And so hopefully this is not crazy. We'll see right here, this is the actual text. And then below it is just a number for each word, right? So we can actually see that the word I just gets turned into the number 2. And if we count down a few, we can see actually vitality gets the number 3, which is kind of funny, if that's actually the right order, unless some of these things are getting dropped. Let's see, somebody said, why aren't you doing 3 splits, train, valid, and test? Oh, this is a great question, and we will get into it in a second. Yeah, the short answer is that Keras gives you a very nice way of automatically generating validation tests. and we'll talk about why that's important in a second. Yeah. So for all the folks who are like, wait, validation test set or validation sets, you are so right, and we will get there. Yeah. But right now, just think of this idea of we have a study guide and we have our test, right? Okay, cool. So now that we have encoded our we've encoded our words into numbers, and now we're going to do something that is we touched on earlier, which is how long are all of our inputs. And so something that we can do to start is we can import NumPy as NP, and let's just get the mean length of all of our sentences. So we've already tokenized and turned them into numbers. And what we can do is we can say length of t for t in xtrain encoded. And so what this is doing is we're just saying get every single one of our encoded sequences, find out how long it is, and then take the mean of all those lengths. So this will tell us the average length of a sentence. Another thing we can do is we can actually just say, let's grab this out and say sentence or review lengths. And so we can take the mean of the review lengths, but then we can also actually do a histogram. So we can say from matplotlib.pyplot as plt, or import matplotlib.pyplot as plt, and we can say plt, and we can say plt hist for a histogram. We can pass in our review lengths, and boom, there we go. So we can see both the average length of a sentence or of a review, and we can also see sort of this distribution here. And this is actually really, really common in NLP, is you will have most of your samples or most of your documents are going to be really short, and then you have some that get really, really long. And this poses a challenge for us because, remember, we're going to have to make everything the same size. And so if we wanted to use all of these, we'd have to make every single review 800 words long, and we just add a bunch of padding. And that's really, really inefficient. And so what we can do here is we can actually just say, we're going to cut things off after, say, 100 words. And I think for this, that's what I'm going to pick. So we have, you see, 76 is like the average. And so if we say 100, that still allows in most things will be totally whole, but we will chop off the really, really long reviews. And kind of the assumption here is that if we are able to see, I'll get rid of this. If we're able to see in the first 100 words where it's going, then maybe we don't have to look at the kind of the 101st word or the 800th word. And ultimately, the reason we do this is just because it is really, really expensive and takes a long time if we kept every single word. So we'll import a tool from Keras called pad sequences. So we'll say from Tensorflow, can I spell, .keras, pre-processing, .sequence, because we're already working with sequences, we'll import pad sequences. And we'll define a big variable or constant called max len, and we'll say 100. So we're just saying we're going to cut off all of our reviews after 100 tokens. This is a minor note, but I am importing things when we start to use them because I actually want to explain, hey, this is why we have to import this. This is what it's for. If you are doing your own thing and you already know what all these libraries are, it's very common to do all of your import statements at the very top. I'm just importing them when we use them because I think it's helpful to understand, oh, this is why we imported this line. But if you see examples of tutorials where they have a big block of imports at the top, that's pretty normal if you already know what they all do. Okay, so we have a maximum length, and now we can actually pad all of our sequences. So we'll say xtrain encoded. So we'll overwrite this variable, and we'll say pad sequences, and we'll just pass in our original train encoded, and then we'll pass two different values. We'll say max len, and we'll pass our max len variable. So this will say, if it's longer than 100 characters, you have to drop off the last ones. Oh, bye, Adam. It was great to have you here. Talk to you later, man. And then the final thing we'll say is padding equals post. So padding is this idea of if we only have 5 words, well, we need to feed something into the model that is the same size as everything else. And so we'll just add a bunch of zeros at the end. And we can take a look at this and see what this looks like. So we'll do this for our X, our training X, and then we'll also do this for our test X. This is also, I think I mentioned this before, but once you get into these bigger models, we often use the variables X and Y, and X is always our input, and Y is always like the target that we're trying to predict. And this just comes from basic algebra where you have a function and X is your input and Y is your output of the function. But it's good to, we could replace all of our X's with input for training and output for training, but we just use X and Y as abbreviations. Then we'll say pad sequences, and we'll pass in xtrain encoded, and then we'll pass in the same values of max len, and padding equals host. And now just to reality check us, we can actually take the mean after we do this, the mean length of each list of tokens for t in xtrain encoded. So this is after we have normalized everything to a length of 100. And so if this works, then we should expect that mean to be 100, right? And it's 100, we're in business. Oh, you are so right. It should be x test encoded. Thank you for catching that bug. I'm sure that would have confused me later. Yeah. No, I really appreciate it when people call out little bugs that I'm typing because, I am, as they say, doing it live. And so I definitely honestly, I'm surprised I haven't made more mistakes already. Okay, so we have at this point really prepped all of our input, right? I guess we can actually just take a look at the first thing here. And this is a great example. So all of these are actual words. And then this is where we start using padding, right? Because our first review was not actually that long. So we added a bunch of zeros just to say, basically telling the model, don't worry about this stuff, right? It's not important. Okay, so we basically have prepared all of our input data, but now we have to do a little bit of special preprocessing on our output data. So currently it's in a format of just an integer label, right? So we saw the value for, I think we say y train, if we just get the first value, it's just 5, right? If we get the second value, it's just a 1. And this is fine when we're using simple models that sort of do a lot of help for us, and they will treat those as categories. But when we are working with these bigger models where we have to set up a lot of the things, we have to do some pre-processing and what's called one-hot encoding. So the way these models actually work is they don't just try to predict what class it is. They don't just try to predict how many stars does it get. What they actually predict is what is the probability it got 1 star. What is the probability it got 2 stars? What is the probability it got 3 stars? What is the probability it got 4 stars? And what is the probability it got 5 stars? And then it will check and see, okay, which of these probabilities is the highest, and that will be the prediction. So that means that it actually wants a label for each of the possible classes it can be in. And we can generate this pretty easily with this tool from Keras called toCategorical. So we'll say from TensorFlow, TensorFlow.keras.utils, we'll import to_categorical. And we'll take a look at what this does. So we'll just say y train encoded, and we'll say toCategorical, and we'll pass in y train. And then we'll just print out, we'll look at y train, the first line, and then we'll also look at y train encoded, that first line. Oh, this is interesting. That's kind of funny. Let's do multiple examples. Let's do 1 through 10. Let's do 1 through 10 here. We get as our, so the sort of the upshot here is that, wait, the y train 0 is index 302. Oh, I think I want to use, let's see, will this give us anything better? Okay, here we go. Oh, that's funny. Okay, so some weird series syntax stuff going on here. What you can see is that our numbers here line up with which index is getting marked. And this is really similar to our vectorization, right? It's like, okay, if you are index 3, then just go 0, 1, 2, 3, and mark it as a 1. If you're index 5, go 0, 1, 2, 3, 4, 5, and we'll mark the 5's place with a 1. And so this just makes it easy for the model to predict all of the classes separately, and then you can see which one has the highest probability. This is just one of those things we do to sort of make the math work out nicely. One minor detail to note is even though that we've been using 5 classes, we get this zeros place, which is just sort of a default behavior. And so we're actually going to be predicting out 6 classes. I think we could actually go back and filter out the zeros, but it's easy enough. So we'll just remember we're actually predicting out 6 classes in this scenario, even though we only have 5 stars. Good stuff. Okay, so now we've prepped, I guess we prepped our training. We'll also prep our test. So we'll say y test encoded. We'll say to categorical, and we'll pass in y test. And yeah, that should look normal. Okay, we've now done all of our prep. Remember, this is something I said at the beginning, is that the majority of your work as a machine learning engineer is just preparing your data. And we have finished that part, and now we get to bring out some of the fun guns and actually use and play around with Keras. So we're going to import a whole bunch of layers from Keras and build a model in layers. So the first thing we'll do is we'll say from Keras, from TensorFlow Keras, import sequential. And so all sequential means is that we're going to have multiple layers that run one after another. And we can say model equals sequential. So this creates a sequential model for us. Now what we're going to go do is go through a series of adding layers to our model. And so this is just layers of math of how you transform your input data through until you get your output prediction. And the first thing that we're going to use is what's called an embedding dimension. Now, embedding is like a really, really deep topic, and we could really talk for a long time about it. But ultimately, embedding is a different kind of vectorization. I really would love to do like 3 days just on embeddings, but the simplest way of explaining it, I think, is that every word gets its own sort of unique representation. And so let's see if I can actually pull up the king, queen, man, woman graph. Word embeddings, king, queen, man, woman. And there we go. Okay, yes. So this is an example that is often thrown out for word embeddings. And apologies for the prevalent use of gender here. There is also really cool work being done on removing gender from word embeddings, so that's very neat. But basically what we have here is a couple vectors, right? And so it's without thinking about it too much, imagine this is just a graph. And so this might be point 0, 1, and this might be point 1, 0. And this might be point 2, 0, and this might, 2, 0, and this might be point 1.5, 1, or something like that. The numbers here are unimportant, but the meaningful thing here is that these numbers kind of give you some conceptual understanding of what the word means, right? So you could literally say king minus man plus woman equals queen. Okay, these things are kind of annoying me. Open image, a new tab. It'll probably be small. Okay, but so what you could say is you could literally say take the vector representation of king, subtract the vector representation of man, and then add in the vector representation of woman, and you would actually end up with the word queen, right? And this is really powerful because it is a conceptual, it's both numerical, but it's also conceptual, right? Before, the numbers we were assigning to our words were really kind of arbitrary. We just picked 1 for I, and we just picked 2 for the, and then those numbers didn't really mean anything. Maybe they actually meant something about frequency, but they didn't mean anything conceptual. And when we use embedding, we can actually get conceptual understanding of our words in numbers. So that's a little blurb about embeddings, but know that I would love to do I'd love to do a week just on word embeddings. And maybe that is, maybe there's another time where we'll actually make that happen. So we're going to add an embedding dimension. So we'll say from TensorFlow .keras.layers, and we're going to be importing a lot of different kinds of layers. We will import an embedding dimension, and we'll import embedding. And so now we can add an embedding dimension to our model. So we'll say model.add embedding. And there are a few things we have to tell our embedding dimension. First, we have to tell it how many different kinds of words to expect. And so we can pass in our vocab size variable that we already defined. I think right now we picked 10,000, so we'll say we'll just deal with 10,000 words. The other thing you have to pick is what's called an embedding dimension. So going back to our example where we had just a two-dimensional graph of man, woman, king, queen, that was just 2 dimensions, right? But often in machine learning, we can get really good results when we make our embedding dimensions kind of big. So maybe we say embedding dimension is equal to 50. That's maybe a good starter size. So we'll say, go from all of these words and give each of them an embedding of 50 different numbers that represent what they are conceptually. And then the final thing that we have to do is tell it how long our sentences will be. And of course, we've already defined our max length. So we can say input length is equal to max len. Okay, awesome. Now, before we do any more work, we're going to do what's called generating a model summary. So this is kind of, it can be difficult to parse exactly what this does to the model, but we have this handy dandy method called summary that shows us a map of what the model at this point looks like. So right now, all that we see is that we have an embedding dimension or an embedding layer that will turn our individual numbers into sort of conceptual representations of our words, right? And that's the only layer we have. And you know, on some level, this is fine, but we ultimately, before we do anything else, we need to convert this into an actual prediction. And usually, to generate our final prediction, we'll use a layer called a dense layer. And really, the way to think about a dense layer is it is basically just logistic regression, right? So we're creating this embedding layer, and then we're sticking on the end one final layer of logistic regression. So we'll import a dense layer in addition to our embedding layer. What we'll do here is we will say model add, we'll add a dense layer. And remember, our final output, there were 6 possible values. And so we'll say 6 is the output size of that dense layer. And then we also have to pass in what's called an activation layer. So this is basically determining how do you draw your threshold. So remember earlier when we were doing this kind of manually, our thresholds were if you have a sentiment greater than 0, then you're positive, and if you have a sentiment greater than 1, you're a 5-star review. If you have a sentiment of 1, you're a 4-star review, and we kind of picked our own thresholds. But the activation layer gives you a way of sort of dynamically picking a threshold. And so we'll say our activation layer is equal to, we'll use an activation layer called Softmax. Now, Softmax is a really, really common activation layer you'll see. And let's actually look up Softmax function. I want a graph, y'all. Give me a graph. Okay, here we go. This is an example of the Softmax function. And so what you can see is it takes our input values. Remember, we could have sentiment that was really high or really low, and it then just turns them in to either a -1 or a 1. And so that all that's doing is it's just saying sort of like the most likely you could be is like 100% up at 1, or the least likely it could be is down at 1 or down at -1, which we'll kind of think of as being, you know, it can't happen. So that's a Softmax activation layer. So now we can actually run this summary again, and we can see that we've added another layer. So our first layer is an embedding dimension, and that gives us this output shape of 100 different words that maximum have, or that have 50 numbers that represent each word. And then we have this dense layer that will generate this this sort of output of 6. But before we do that, we actually have to do one more thing, which is what's called pooling. Oh, somebody said, when you showed the embedding, canned was 1. I was 1. If we edit the data set just a little bit, does the embedding change completely? Oh, this is a great question. And the answer is yes. So something that you will often do is you will actually save your tokenizer. So something we can actually look at over here is we did this tokenizer to, where did we tokenize? We said fit on texts. And when we did this, our tokenizer actually built up a word index. So we can say word index, and we'll actually see a giant dictionary that just maps individual words to numbers, right? And if you regenerate this and you change your data set and you retrain fitting on texts, then this could change completely, right? In practice, it usually doesn't change that much, but you have no guarantee that the numbers will be the same, right? And so what you can do is you can actually save this tokenizer so you know you'll tokenize in the same way every time, because regenerating it can be, you know, kind of a lengthy process. Okay, awesome. So getting back to our model here, you can see the output of the dense layer. Okay, somebody asked what is the dense layer, and the dense layer is basically like logistic regression that we implemented yesterday, where you pretty much just add up all of the weights and you see if they're greater than a threshold. And so you will sort of take your inputs, multiply them by your weights, and then just see if they're greater than a threshold. So another way of thinking about this is that basically every single different weight has or every single different input has an impact on the output. That's kind of the way that we think about this. Or another, to maybe make this more concrete, it's that every single word can have an impact on whether the whether it's 5 stars or whether it's 4 stars or whether it's 3 stars or whether it's 2 stars or whether it's 1 star. Hopefully that's a little bit clearer of an explanation. Also, y'all, I see that we are about halfway through, and so we talked about this before. Keep telling me if you have questions, and keep telling me if you want me to speed up or slow down. All that's really helpful. We will get as far as we get, but we will get to some interesting things. Yeah, absolutely. Thank you for your question. Okay. So we have our dense layer, and checking the output shape here is really, really helpful. So right now, we have one of the dimensions is 100, and one of the dimensions is 6. So remember, 6 is what we wanted because we have 6 potential output classes. But 100 is still preserved from the fact that we're having an input sequence of 100 different things, right? And so one thing that we can do here is do what is called a pooling operation, which is basically a way of taking all of your different words and kind of merging them together. And so this takes something that could be of a very long sequence and squishes it down to sort of a constant size for us to predict on. Because right now we get this output of 100, and that's going to be too big to actually make a prediction with. So we'll add, I actually have to import this, but we'll add something called global max pool, and we'll say 1 dimension, because this is actually a really important thing to understand, is that text data is kind of fundamentally one-dimensional, right? If you think about like a photo, well, if like or the video stream you're getting right now, I guess it's technically what, like 4 or 5 dimensions, because you have pixels going up and going down, and you also have RGB values, and you also have like audio and time. But maybe a picture is easier. A picture is just 2 dimensions, right? But text is really 1 dimension, right? You only have to kind of follow one line of text in order to get all of the meaning. So that's why all of our things are going to be 1-dimensional. And remember, this is just a way of sort of taking all of the words that we have in a line and sort of squishing them all together. So we'll say model add, and we'll add this global max pool 1 dimension because text is 1-dimensional. And we'll try to generate that. Okay, so this is great. So you see our global max pooling layer takes this 100 term and just gets rid of it. So instead of thinking about having our model having 100 words in a row, we squish them all together so we only have a single representation of all of the words. And there's something really important to understand about this is that when we do this, we lose all our information about order, right? And this is something we looked at yesterday, that we had a bag of words approach where we really didn't care about order. And that might have caused some problems, right? We might have lost some information about, like we threw out the example of it's bad versus it's not bad. Well, bad is still in there, and we might say that's a negative sentiment word, but if you have the word not in front of it, that would modify it, right? And so by doing this global pooling, we're actually getting rid of that sort of context there. And that's the thing we're going to talk about and try to deal with in a second. But first, I want to just get us off the ground. We have a model. It goes from an embedding dimension where every single one of our words gets a conceptual representation. And then we squish all those representations together with our max pooling. And then finally, we have a dense layer that's kind of like logistic regression that we did yesterday. And we output these 6 values of, does it have 1 star? Does it have 2 stars? Does it have 3 stars? Does it have 4 stars? Does it have 5 stars? Okay, so we're going to get training and testing in a second here. One last thing I want to call attention to is this number of total params and trainable params. When you get in deep into the world of machine learning, this number of trainable params becomes really important, because really this is like the size of your model's brain, right? And if you have a very, very small model with a very small brain, then it is really easy to train, and it will probably train pretty quickly. But the trade-off is that it might not be very smart. So right now our model has 500,000 params. And just for context, let's look up how many trainable params Lambda has. So we were just talking about this model Lambda that is this chatbot, right? How many trainable params or parameters? Params is short for parameters. Does Lambda have? Okay, this might not be public. Never mind. Also, Lambda is spelled funny. Okay, there's another model called BERT, and BERT is similarly like this really powerful big language model. How many trainable params does BERT have? Okay, there we go. There's a good number. 110 million trainable params. So that is what I would call, at least compared to what we're doing, a big model, right? That model has a really big brain, which means it needs a lot of data to train on, and it's going to take a very, very long time to actually become smart. But once it's there, it can be really, really intelligent. And so comparatively, our model here has 500,000 params, which kind of sounds like a lot. And, in some sense, it is a lot. If you compare this back to our original model, where we just looked at the 10 positive words and 10 negative words, that model only had 20 parameters, right? That was really all of the parameters it had was those 20 words. And so you think about it that way, this is quite a lot, but it's still pretty small compared to those big models like BERT. So knowing how many trainable params your model has is a really, really helpful thing to understand, because your data has to basically teach every single one of those neurons what to do. Okay, I think I've filibustered for quite long enough, and we will get in and we will actually start training a model and seeing how it works. So we have our model. Actually, before we do that, we actually have to do something called compiling it. So we will just say model.compile. And we'll pick a couple of parameters here. I won't go too deep into these parameters. In a lot of cases, these will be the parameters you want. So we have to pick something called an optimizer, which is basically what kind of math does it do in order to update its weights. So remember, this is a whole process of it learning what things are good and bad and what kinds of weights it should have. And so we'll pick an optimizer called Atom that's really common. I won't go too deep into the math there. We'll also pick what's called a loss function. And in a second, we'll talk a lot more about the difference between a loss function and accuracy. So a loss function, we're going to use one called Categorical Cross-Entropy. And again, we could, all these things, we could spend a whole day talking about categorical cross-entropy. But I think the easiest way to understand categorical cross-entropy is the model will give certain probabilities for all of our outcomes, right? It'll say, if it thinks it was a 4-star review, it might say there's a 90% chance it's a 4-star review. There's a 5% chance it's a 5-star review. There's a 5% chance that it's a 3-star review. And I'm going to say there's a 0% chance that it's 1 or 2 stars, right? That's going to be its prediction. And what categorical cross-entropy basically says is when you tell it what the actual result was, how surprised is your model, right? And so, for example, if it said, if the truth was it was 4 stars, your model basically wasn't surprised at all, right? It said that 90% it was going to be 4 stars, and it was basically right. On the other hand, if it actually ended up being 3 stars, your model is kind of surprised, right? That was still something that it gave a decent chance of being, it still said that's possible, but it'll be a little bit surprised. And on the other hand, if it actually was a 0-star review and your model said that it was a 4-star review, then your model is going to be very surprised, right? And so that is what our loss metric looks at, is basically how surprised was your model at what the actual truth of the prediction was. Again, complex concept. If you have questions about that, we can talk about it more. But then finally, we're going to add one more thing called metrics. And this is where we're going to add accuracy. So we'll just pass in the word accuracy, which was, of course, the secret word for yesterday. And this is just another thing that will get reported. So remember earlier I said it's going to give us probabilities. It's going to say there's a 90% chance that it is 4 stars and 5% chance that it's 0 stars, right? And that's really helpful. But ultimately, we just care about, well, what was your actual guess, right? And so accuracy just tells us whichever one it gave the highest probability, was that actually right or wrong? And so that's what the accuracy metric will give us, just like we computed yesterday. We have some questions, which is great. I'll check in with that. And hopefully some of this stuff can sink in. Question, there's a chess engine that debugs a game called AlphaZero, and it generally gets better over time, and games which are played by top players are run in it or added in it, IDK about it, and it gets more ideas and gets better over time. So my question is that can models add the output to its input to improve accuracy? Oh, this is a great question. Yeah, y'all know what's about to happen. Oh, okay. Somebody asked where can I find previous parts, and I will drop the GitHub. So there's a GitHub link that has all our previous code here. And then additionally, if you want to, you can jump into the current notebook I'm working in, and you can follow along with the live stuff we're coding right now. Okay. So yeah, we'll back up and zoom out a little bit, and we'll talk about the different kinds of machine learning. So the biggest class of machine learning that we do a lot of is called supervised learning. And this is where you have sort of labeled data, right? And so in our case, we're doing supervised learning because we have this corpus where we have Amazon reviews, and then our labels are really the number of stars, right? And so we're trying to predict a label that we already know, right? So that's great. Supervised learning is easy. There's also something called unsupervised learning that honestly is a little bit murkier, but the easiest example that I throw out is clustering algorithms. So say you have a bunch of marketing data and you're trying to put all of your customers into clusters and say, what are the unique groups of customers? And you can use clustering algorithms that we consider unsupervised because you don't have any labels. You're really asking your model to come up with the labels for you. And then finally, there is this third class called reinforcement learning. Yes, somebody mentioned it. And reinforcement learning is where your model basically can play out its predictions in real time and see how it went and then learn from that, right? And so reinforcement learning is really, really good for video games, right? Because what video games are great at is you can have your model actually play against another model or against a human and sort of get that data and feedback and have a feedback loop, right? This is tough with some other things. Like, for example, it's hard to do reinforcement learning with sentiment analysis because ultimately the sort of ultimate judge of whether or not the sentiment call is correct is humans, right? And when you need a human on the other side of it telling the model if it won or not, that's always difficult. But in games like, for example, chess, you can have models play against each other and you can see who wins, right? So when your rules are very clearly defined, you can do a thing called reinforcement learning. Reinforcement learning in a lot of cases is not all that different from supervised learning, but the supervision comes from the game itself, right? So for example, you could have a model that basically the input is the two-dimensional chessboard, and the prediction it makes is what is the best possible move, right? So you could see a potential chessboard and it could predict, oh, I think I should move the knight to f6 or whatever. And what you can do is after you play a game, you can see if you won or lost, right? And if you won, then you can say all of those moves that I made, they were probably pretty good and treat those as like good test cases. But if I lost, then basically say all of those moves that I made were actually not great decisions and try to do something else next time. So that is a really, really brief overview of reinforcement learning, but it is, I think, closely related to supervised learning, which we're doing here. The difference is your labeling can come from did you actually win or lose, and so you can do that really fast and automate it. Hopefully that makes some sense. Somebody asked, how much of theory should I know before I start coding related to machine learning? This is a great question, and this is something that I think it gets back to this question of do you want to go fast or do you want to go far, right? And I think that if your goal is to put together a couple of projects and be able to use some pre-built libraries, then the answer is really not that much, right? You could look up some tutorials on using scikit-learn. I mean, really what we're doing here is kind of a cross between the two, but you can use some very basic models without much trouble, without knowing much theory. The question is, if you really want to be like a machine learning engineer and you want to start using these more complicated things and tackling more complicated, harder problems, then some of that theory becomes more important. And so learning about things like statistics and matrix algebra at that point, and even actually really computer science, where you learn about sort of running time complexity, those things become more important if you want to tackle really, really hard problems. But if you're only interested in tackling sort of, your run-of-the-mill problems, then actually there are a lot of tools that you can use without really knowing that much theory. Somebody mentioned Andrew Ng's course on Coursera, and I would totally second that. It's a great course. I would say the documentation for scikit-learn is good. I also, to sort of go back against what I just said, I think that finding an actual example problem that you want to solve is a really, really great way to learn, right? So if you have some data that you have some context on, and you just want to try to solve that, that can really be a great way to learn only what you need to learn to tackle that problem. Somebody said, I started that course, was not sure whether I needed it or not. Yeah, I mean, it is a really tough call. And I think that, I think I'll just reiterate what I said, that for a lot of things that you'll do, like doing all of that theory will be overkill. But if you want to go far and you want to get your hands on really difficult problems and cutting edge stuff, then building that foundation is important. And yeah, I think Andrew Ng's course is a really great course that kind of introduces you to, some of the math and some of the statistics, and all that stuff is great. Okay, jumping back to actually coding. But you know that I love a good tangent. Jumping back to coding, we've just compiled our model and we've passed in a couple of things. So we have our optimizer, which basically tells it how do you update your weights. It has a loss function, and the loss function is really important because that's how it really decides how wrong am I, right? And so we use categorical loss entropy that basically says it's going to make a prediction and how surprised is it by the truth. And then finally, we have this metrics, which will add in accuracy, so we can just see how accurate was our model. Did it get it right or wrong at the end of it all? Okay, so we have compiled. We'll run that so we can compile. And now we can finally get to training our model. Okay, so we've already done all of our prep work. And so we can say model.fit. And we'll pass in first our input. So we'll say y train encode. And second, our output. So y train encode. Then we're going to pick something called epochs. And this is something that we talked about. Somebody mentioned it a little. I think Aerosol Cam mentioned it a little bit yesterday. And an epoch is going through all of your data once, right? So the way that these bigger models work is that you will take some of your data and you'll show it to your model, and it'll learn from that. And you'll take another chunk of data and show your model that, and it'll learn from that. And the reason you have to do it sort of in these chunks is because you have so much data that you can't even fit it all in memory at one time. So you kind of break it up into these little sessions called batches. But what happens is, okay, your model trains a little bit on batch number 1, and it gets good at that. And then it trains a little bit on batch number 2, and it gets good at that. But it might actually become worse at batch number 1. And so you end up doing is you run through all of your batches several times. And so when you get through all of the data that you have, that is called an epoch. And normally we'll train a model for several epochs. So this is kind of like they'll go through the entire study guide once, and that's an epoch. And then you'll go through the entire study guide again, and that's a second epoch. And so we're going to pick how many epochs we do. And because we're just kind of playing around, I'll say 10 epochs. 10 epochs is not nothing, but it's like a pretty short training period for bigger machine learning problems. So I mentioned batch size before, and that is basically how many examples does it look at once? Or, if we're going back to our study guide example, it's like how many questions are on each page? So how many questions are you testing yourself on at once? And we will set a batch size of 64. Normally, this is something that if you're dealing with really big data like images, you'll set your batch size pretty small. But if you're dealing with small data like just numbers or words, you can make it bigger. And usually speaking, the bigger your batch size, the faster it will be to train. So you can think of this as if you can cram 50 questions on every page of your study guide and you can speed read, then you can study really quickly. But if you have just 1 or 2 questions per page, you're going to spend a lot of time turning the page, right? Not a perfect example, but that's maybe to extend the metaphor. Great. So we'll define this, and now we will run it. Boom. And you can see it's running through here, and it is giving us accuracies, right? Oh, boom, look at that. So it ran through all of our data once, and it took just 1 second. Then it ran through all of our data again, and it gave us did 1 second. and so on and so forth. And you can see that it reports both the loss and the accuracy, right? So the loss is what it's actually using to tell itself, do I need to study this concept more? Did I get it right or wrong? And the accuracy is nice because it just tells us what percentage of the time did it actually predict the right number of stars. Now, a few things to look at. First of all, over time, it got better, right? So we started with a pretty high loss of 1.5, and at the end, our loss dropped all the way down to 0.62. We can also see our accuracy went up, right? We started basically at the end of our first epoch, it was basically a coin flip as to whether we got the right answer. And then by the end, we get an accuracy of 79%, which if you remember, I think our best accuracy with the logistic regression model yesterday was like 77. So we're already doing better, right? Or are we? Dun, dun, dun. Okay, this is part of our journey on understanding the pitfalls of some of our machine learning models. And remember, this is the accuracy on the study guide, right? And so the problem here is, well, what if our model is just memorizing the specific questions, right? And we do have a test set, right? And later we will go look at a test set. But the problem is if we actually show our model the test several times, then it will actually just memorize the test as well. So somebody mentioned this, where we have 3 different layers of data. And the first one is our study guide, right? That's our training set. And then the second set that we have is called a validation set. And so that is when we're still learning, just being able to check in on data that it did not actually see already. So maybe a good way of thinking about this is that a validation set is kind of like a quiz that you get before the test, right? So it's not questions you'd seen before when you were studying, but it is not the big test set at the very end of the semester. And so we could split up a separate validation set ourselves, but we actually don't have to. Keras makes it really easy to, as it's training, generate a validation set. And so what we can do is we can add in another parameter here called validation split. And we can add, say, 0.1, and that'll just say 10% of our data will get withheld to be a validation, to be our validation test set. So that's kind of like, hey, give it the study guide of 90% of the questions, but then before we do the big test at the end, give it a quiz at the end of every studying cycle of 10% of the questions. And so now if we run this again, we'll get both the loss and the accuracy, but then we'll get 2 additional numbers, which are the validation loss and the validation accuracy. And so a couple of things to note here. One is, a couple of things to note here. One is we are now getting the validation loss and the validation accuracy, just like we said. Another thing to call out is that because we defined our model up here and compiled it up here, when we ran the fit function a second time, we actually started with a model that was already trained. So you can see we were already starting at 81% accuracy. And so if you want to kind of start over again, you can come back up here and run it and then fit it again. And you can see we're getting pretty good accuracy. At the end of this, you can see that our validation accuracy is actually worse than our sort of normal accuracy or our training accuracy. And this should not be a surprise if you were thinking about our analogy, right? That it's like, okay, if I told you you got 90% on the study guide and then you only got 80% on the quiz, like this probably wouldn't be surprising to you because it's like, well, yeah, the study guide has the answers attached to it, right? Like I could just see them. And so this is what we call overfitting broadly. And we're going to use a tool called plotting our history of training in order to see this a little bit better. So what we'll actually do here is, how do we want to do this? This really is me doing it live here. What if we actually say, instead of 10 epochs, let's say we'll do, it trained pretty quickly. Let's do 30 epochs and just double check what's going on. Okay, yeah, this is good. I'm gonna stop that. Boom, okay. So we're gonna create a fresh model, and the output when we're fitting is something called the history. And so we'll just store the history in a variable. Tensorboard is really cool. I don't think we'll get into Tensorboard, but Tensorboard is a fun way of visualizing your model, no doubt. Okay, so we're getting those data on the accuracy and validation, the loss and accuracy and the validation loss and validation accuracy. And you can go through and you can see what's happening, but it sometimes is actually easier just to graph it out and see how this changes over time. So now that we grab the history in that model or in that variable, history itself is like its own little object, so it's a history object. But we can, I think we already imported matplotlib, and so we can just literally say plot. We'll take history dot history, and we'll plot the loss. But then we'll also take history.history and plot the validation loss. And we'll add a legend on there. We'll say the legend is the training loss and the validation loss. And we can just say plt.show. And this is a great map. This is a great graph. I misspelled legend. Okay, it was almost a great graph. Y'all, I'm really having a tough time spelling today. Here we go. This is a great graph. This graph really is this is machine learning. This is, if you are a machine learning engineer, this graph is what keeps you awake at night. So what's going on here? Take a minute. In fact, I'm gonna zoom way in on this graph because it is just so good. And I was hoping we would get a graph like this. So you can see we have our training loss and we have our validation loss. And you can see for a while, our training loss is going down and our validation loss is going down, right? Basically, this is saying the more it studies, the better it does with the study guide and the higher it scores on the quiz, right? But then there is a point, and it maybe is around 10 epochs, maybe 15 epochs, where it keeps doing better on the study guide, but it actually starts doing worse on the quiz, right? And yeah, I mean, people are calling this out, where you see those things cross, and you see that we stop getting better at the quiz, we stop getting better at our validation test set. That is where overfitting starts, right? Right around here in this region is where the model says, oh, wait, I keep getting asked the same questions. I can just memorize them, right? And when your model figures out it can just memorize the questions off the study guide, that is when it starts doing bad on its quiz, right? You can see it actually was improving, and then it starts doing worse on the quiz than it was earlier. So this is incredible. This is great. This is like the heart of machine learning, and this is the place that I'm really excited we got. Okay, somebody asked about underfitting. Actually, here, let's run through an example of underfitting. So one of the ways we can get rid of overfitting is by just making our model's brains smaller, right? And think about it. If you actually have to have kind of a big brain in order to memorize all the answers to the question, you're just kind of cheating. You're kind of being nefarious, right? And so one thing we can do is we can just say, you get a very tiny brain, right? And so what if we said, what if we said the embedding dimension is 2, right? So every word only gets 2 numbers to describe it. And I mean, I haven't run this test before, but my guess is we're making it sufficiently small. We're giving it a small enough brain that it actually will just not be able to understand like kind of anything, right? And so it will probably actually just be it will not be smart and then get too smart. It'll just never become smart, right? At least this would be the concern. Okay, let's zoom out a little bit. And yeah, okay, this is a great example of underfitting. Is we're hanging out around here and we're just keeping 60% accuracy. And so if we plot this, oh, that's an interesting graph. Okay, yeah. So I guess what's happening here is it does improve a little bit, and the problem is the accuracy never gets above 0.6, right? Yeah, no, literally, this is a great comment. We literally said our brain gets 2 brain cells, right? And so this is underfitting, where sure your validation never gets worse, but it never gets good to begin with, right? So a great question of like, what does underfitting look like? And that's what underfitting looks like. So let's go back to giving our machine 50 brain cells, right? And rerun that again. So how do we deal with overfitting? Because okay, yeah, we don't want this thing where it scores great on the study guide but performs badly on the quiz. Which is what we see here, where it's getting 90, almost 100% accuracy, but then less than 70% accuracy once we give it a quiz and data it hasn't seen before. But we also don't want to give it 2 brain cells and just have it be done the entire time, right? And so we're going to explore a couple tools in the toolbox to try to make it not overfit quite as much. Although actually, before we do that, I think we're actually gonna make it overfit more, or we're gonna give it some more power before we try to limit its power. So far we have just been doing a bag of word approach, right? But something that we talked about is the fact that we don't actually we're not taking into account the relationship that words next to each other have, right? So there was another kind of layer we can add that basically does a rolling window of looking at words next to each other and do they have an impact on one another, right? So we talked about this idea of, well, if you have the word not in front of the word bad, then that takes on a totally different meaning than not and bad separately, right? If I said, it's not bad, that's one thing. But if I said, not to worry, it's bad, like that takes on a different thing. And it's because the word not is not right next to the word bad. I may not have explained that great, but yeah. Somebody mentioned you can start manipulating hyperparameters. And hyperparameter is a great word to throw out. And hyperparameters really is like things like our embedding dimension, that is a hyperparameter. Our actual parameter is sort of the weight of, like we said earlier, like is this a positive word or a negative word? That's an actual weight. But the embedding dimension, basically how many brain cells does it get, that is a hyperparameter. Okay, so somebody mentioned you can use Optune to automate hyperparameter tuning. And yes, so there are lots of ways that you can sort of have a thing sort of try out a bunch of different kinds of models and see which one works best. You can do this yourself. There is also something, and this is shameless plug for the company I work for, but there's a thing called Google AutoML that is really powerful that will do hyperparameter tuning for you, where you can basically just give it your data and it will churn through it and it'll try to figure out, yeah, we think this is the best kind of model for you to use, and just kind of give it to you. So there are ways of doing that. We're not going to look at that today, only because it can be really nice and informative to actually try to change these things yourself. Hannah says not SpawnCon though. Yeah, no, not SpawnCon at all. I'm not. I mean, all I'll say is that Google paid for this flower crown, Okay, so we're going to try to add what's called a convolutional layer that looks at words next to each other, right? And maybe we can actually look up the documentation for this. Okay, what if we look at, so it's a conv1d. Oh, I literally already have the documentation pulled up. Boom, where are you? Reading documentation is great. So a one-dimensional convolutional layer. This creates a convolutional kernel that is convolved with the input layer over a single spatial or temporal dimension to produce a tensor of outputs. If use bias is true, bias vectors is created and added to the outputs. Finally, if activation is none, it is applied to the outputs as well. So this is, I'll be honest, great documentation if you already know what a convolutional layer is, but it is not great documentation for learning what a convolutional layer is to begin with. But so returning to maybe one of our example sentences before we throw this in there. Okay, this is great. So y'all can still read this example sentence where it says, I have bought several of the Vitality Canned Dog Food products and have found them all to be of good quality, right? So what if we had a convolutional window of 4? Okay, so first we would look at these 4 words together. I have bought several. It's like, okay, maybe not really positive or negative. Have several bought of. That's like the next window. Okay, maybe not that big, or maybe not that positive or negative. And we can continue this window, sliding it down. And so now we'll look at bought several of the vitality canned. And we'll keep sliding down. And I'm trying to see if we can get a good window. Okay, I changed my mind. Let's say our window is 6. And so if we have like our right here, it's 1, 2, 3, 4, 5, 6. And it says them all to be of good. And then we slide down one more and it says all to be of good quality, right? So suddenly that window that our model can look at, that actually is really meaningful, right? In a way that if we just look at the individual words and we have all, not really positive or negative, good is like a kind of, it's definitely kind of positive. But if we get that whole window of all to be of good quality, suddenly that tells us something a little bit more powerful about the whole thrust of the whole sentence, right? And so I want us to try adding in a convolutional layer here. Now we're still using a very small amount of data, and so it might not actually train particularly well. So warning, this might actually, it might take away something, but we can throw it in there. So we will say convolutional 1 dimension, and we will add to our model, conv 1 dimension. And now we're going to have to put in some parameters. The first parameter we'll put in is the number of filters. And this is basically the, what is the size of the output sort of per window, right? And so let's say we started with a dimension of 50. What if we continue that and say the output dimension is 50? Then we'll look at what's called the kernel size. And this is basically how big the window is. So this would be like, how many words do we look at once? And so what if we start with something modest and we say something like 4, right? So it'll look at sort of 4 words at once. And then the kind of last important thing that we want to look at is the number of strides. And so this is, how far down do you move your window every time? And normally we actually just want to set a stride of 1. That's a pretty normal thing to do. And then finally, if we want to, we can add an activation layer, and let's do it just for the heck of it. And so the activation layer we'll use just so we have some diversity in here, we'll use a Relu activation function. So this is, I'm just going out there so you can hear different activation functions. But so Relu is an abbreviation that means rectified linear units. And I'll pull up a graph of that. Relu graph. And this is basically a Relu graph. All it basically says is if the input is less than 0, make it 0. But if the input is greater than 0, make it whatever it was before, right? And I feel like the theme of today is, this could be an entire session is just on why we use different activation functions. But one of the important things here is that when you're using an activation function, it's really important that you have some kind of nonlinearity. And so what that just means is that you can't have a straight line as your activation function. If you have a straight line as your activation function is kind of useless. So you need some kind of nonlinearity. In our logistic function, here's a good comparison. This is basically a logistic function, and it has a particular kind of nonlinearity. And this is a Relu function, and it has a different kind of nonlinearity, but neither of them are just straight lines, right? What is nice about the Relu function is that you can actually get big numbers. So with the sigmoid or the logistic function, you can never get a number bigger than 1 or a number less than -1, or sometimes you even bound it between 0 and 1. And what that means is if you run something through a bunch of those functions, you will always end up drifting towards 0. And this is like, again, I will repeat it, we could do a whole session just on this concept. But if you have a bunch of sigmoid functions, what you'll end up doing is you will end up cramming all of your numbers closer and closer to 0, and it will make the math kind of useless. And this is what we call the vanishing gradient problem, which is a big topic of conversation. What the Relu function does is because you can actually get really big numbers, it can help you solve this vanishing gradient problem. Somebody mentioned leaky Relu, which is sort of a variation on the Relu function. But so we use that as our activation. And so that gives us our convolutional layer. And yeah, let's run that and give it a shot. So one thing that's really neat is that you can see our original embedding dimension added 500,000 parameters. Our convolutional layer only adds 10,000. So our convolutional layer is comparatively kind of small. Another minor thing to notice is that our convolutional layer puts out sort of 97 different words, so to speak, or 97 different steps in our sequence. And maybe you can guess why that is. Maybe I'll just explain it. Is that when you have that sliding window, because our window is 4, you can't actually have as many outputs as you have inputs, right? Because there will be a little bit at the end where you basically will have sort of like the last word will only appear in a window once. So that's why our output of the convolutional layer is it's going to be basically the window size minus 1 fewer than the input size. Okay, so I just recompiled that again. But now we can try fitting on that, and we'll use kind of the same setup. So one thing you notice is earlier we were training right around like 1 second and 1 second per epoch, and now it's taking, at least the first one took a little bit longer. And what you can see is, hopefully this becomes obvious, is we still have kind of the same problem. This does not, it gives it kind of more capacity, and our accuracy, our validation accuracy does end up going up a little bit, but it is still way different than our training accuracy, right? It's still getting basically 100% on the study guide, and it's doing worse on the validation accuracy. It's doing better on the validation accuracy than it was before, but it is still not doing as good. So if we graph this, we should still be able to see our problem of overfitting. Oh yeah, there is a great graph for overfitting, right? You can see it gets better, and then it just starts getting worse, right? Even as our training accuracy is basically 100%. So we've made our model a little bit bigger. It can now take into account these two words are next to each other. Maybe they mean something. But what we have not done is fix this problem of overfitting. So I'm going to introduce 2 tools to deal with overfitting. One of them is called dropout. So dropout is a powerful idea that, again, I'll reach for a metaphor here, but it's kind of making your model wear glasses that are fogged up. And what that basically means is if your model has some randomness and sometimes it can't see things perfectly, it makes it harder for your model to memorize things, right? And so what we'll do is we can scroll back up here and we can add, actually, we'll copy this down because I like having this as an example of this is the model that overfits. But so now we will get a dropout layer. And the dropout layer is really simple. The only thing that you have to tell it is what percentage of things do you drop out. And so it will randomly assign some of the inputs to 0. So we could maybe, after our convolutional layer, say model add, and we'll add a dropout layer. And it's actually very common to put 0.5 as your dropout layer. And we could add one of these to the embedding layer as well. But I'm kind of curious to just see how just adding this impacts it at this moment. So let's grab our training loop again. And we'll compile that. You can see our dropout layer. It does not change the shape, and it has no trainable parameters because all it's doing is just randomly picking some of the neurons to say, brain cell, today you sleep. And so it's a way that your brain can still be big without memorizing the input data. So let's train that. And then we'll also copy down our graphing to see how that works. So notice that even though we're using a very small data set, like 10,000 records right now is actually pretty small, it's already still taking quite a bit of time to run. And part of that is because we're doing it for 30 epochs. And so you see, I mean, we don't want to jump the gun, but you can see similar things are happening. Yeah, it is always a good thing to adjust one variable at a time. This is very good advice. And okay, great. This is about what I expected. So you can see that we are still getting overfitting, but it might be not quite as bad as it was before. So we go up here, you can see it actually jumps way higher, like the training loss up here ends up being, or the validation loss ends up being higher than it started out as, right? And once we have the dropout, it still climbs up, but not quite as high, right? So it's doing a little bit better on the quiz than when it was just purely memorizing things. We could, if we wanted to, even add another layer of dropout after our embedding layer and see if that helps even some more. But so dropout is one powerful tool to try to fight against overfitting, but it is not it's not a silver bullet. And you might ask me, Will, what is a silver bullet? I want a silver bullet to solve this problem. And in machine learning, there is something that kind of always is, more or less, sort of a silver bullet, and that is throwing way more data at the problem. And this is, of course, the moment we're waiting for, where we have like 5,000 records of data. Why can't we just use it all? And so that's what we're going to try to do, and we're going to see how this affects the overfitting or lack thereof. So we have our raw DF here. I'm going to copy that down. Oh, so many outputs. In fact, I'll add a little text box here that says, now we solve all our problems with more data. And we will grab some of our pre-processing steps again. And these pre-processing steps now actually will take quite a bit of time. Let's see. Let's grab this. I guess we don't need to import anything. We'll recreate our train test set, only with raw DF instead of DF. Let's see, somebody said, are we currently using the TPU? Yes, I believe. Yeah, I'm currently using a TPU. And so this is running basically as fast as it can. There's a whole study of which models can you make faster. And so there's actually a big trade-off in some models are easy to parallelize and some models are hard to parallelize. So there's some models that even when you add more hardware, it just can't use the hardware. A lot of the models we're using here are fairly easy to parallelize, but that is a whole subject to itself as well. Okay, so I'm going to rather inelegantly just keep scrolling up and down and copying this. In fact, now that we're using all this data, maybe we make our vocab size, instead of 10,000, maybe we bump it up to 20,000, right? And actually, you know what? In the spirit of only changing one thing at a time, let's say this time all we're doing is adding more data. Just because somebody gave out that advice and it is good advice. Okay, so then we've already done that, and we will do the turning into sequences. This is why it's nice to build just a preprocessed function, so you're not constantly copying code, right? This is not, to be clear, this is not a best practice. Then we'll prep our training data. Honestly, there's actually not a crazy preprocessed amount of code, so we should be able to run that. And this should actually take quite a bit of time because our training set now is quite big. I see we have about 10 minutes left, and so we might be able to train a model before things are done here. And okay, yeah, this was our model without dropout, or with dropout. I'll copy that down. And we'll try to plot it. And hopefully I did not miss anything big. Okay, cool. We successfully pre-processed all our data, and now we're going to compile and train our model. So the compilation it is basically the same model. We're just using more data. And then we'll grab our training loop. Oh, and actually a few changes we're going to make to the training loop. Oh, this is actually something that I promised we would talk about, is saving a checkpoint. So you remember we had this case where it was getting better, and then it started getting worse, right? And so the model we had at the very end was actually a bad model. But one thing you can do is say, hey, if right here it's really good, just save the model in that point in time. And so we're going to add something called a checkpoint. And so what we'll do is we'll say, from tensorflow.keras.callbacks import model checkpoint. And then we'll create a checkpoint and we'll call it, so we'll say model checkpoint. And we'll just pass in a name for the save file. So we'll say my min loss model. And H5 is just a data format for saving a lot of data about models. And we'll say monitor, and we'll say val loss. So as soon as you have the minimum amount of validation loss, we'll save a model. And then we'll say verbose equals 1, just so we can see it happening. And we'll say save best only. We'll set to true, so we only save one of these at most. And we'll also just say the mode is min, so we'll just try to save the one version that has the minimum val loss. And you can add into your training loop, you can say callbacks, and we'll add a list of callbacks that just includes MC. This will save our model when it's doing really well. The other thing we'll say is we're going to bump the batch size way up. We'll bump it to 4096. This is actually a minor detail, but often you will change your batch size in powers of 2. And if you're trying to remember all the batches of 2, you can remember that game called 2048, because all those are powers of 2. Anybody remember that game, 2048? It was really addictive. I would say if we have extra time, I'll pull it up and play it, but we won't have extra time. But okay, so we have a batch size that will speed it up because we have we can sort of look at many questions at the same time. We'll also reduce our epochs to 10 just because I don't know if we'll have enough time to train longer than that. But you know what? I think we're off to the races. Let's give it a go. Oh, this is unfortunate because we're clearly not using all of the data because it's running that fast. Where are we? No, clearly we're not using all of the data. I just say length of that. Okay, yeah, we're still using our small set of data. Thought we're using raw df. Let's do the length of that. So I'm just right now checking. I tried to get all of our data. Okay, so length of xtrain is 426,000. So xtrain is good. And we fit on xtrain. And then, oh, we didn't actually encode it again, and that's why we're using our old encodings. Okay, that's good to know. This is the issue with copy and code, and this is why you should just write a pre-processing script. You know, we did pad them, but we did not actually encode them. So we'll copy that down. Thank you for bearing with me, friends. We are so close to the end to having what might be our best model yet, but we will find out. Okay, so we have to actually use our tokenizer, and that might take a hot minute to run now. We really have been flying today. It really is. I mean, we talked about it, but we really have this week moved at a really fast pace. So I'm curious. I'm actually going to check again on that quiz to see what people have said, because a lot of folks were saying, yeah, this has been sort of a good speed. Here, I'll pop back to my face for a second. Oh, my face that's way too zoomed in. But just to check what the feedback is looking like, because I am really curious to know if for the average person, if this is, you know, if this is too fast or just about right. Okay, so we're now like 20% of folks said it was a little bit too fast, and 80% of folks said it was just about right. I'm going to post this one more time, and if you haven't voted and said, hey, this is, you know, this was a good speed, or I wish you would have slowed down a little bit, then please leave your feedback, because it is really valuable for me, because we're going to do this again, and, you know, I would love for it to be even better. Okay, we've got 4 minutes left on the clock. Let's see if our our pre-processing has run. And so now we should be able to recompile our model, and we should see it actually takes a hot minute to train. Okay, here we go, yes. So this is the joy of, we are running with a TPU, basically the best hardware that you can get for training models, and look at it go at sort of a snail's pace. And this is because every single time that little line makes it across the screen, it's looking at like 400,000 different reviews, right? So we've entered the realm of big data. And I think because we picked 10 epochs, this should be good. We should be able to get through all of our epochs before the end. But we see a couple fun things. So, and this is sort of one of the catches is you'll end up seeing your accuracy go down, and it'll actually be a good thing because you realize the accuracy you were getting before was a lie, right? This happens all the time where you use a better model and you end up getting worse results. And you have to ask yourself, was I doing all of my rigorous statistics before, or is it possible that I was overfitting? But you can see every epoch we go through, we're using that. Somebody said, I think you need to set it up to use a TPU or GPU. Yeah, we ran through that just a second ago. You can go through and you can look at your run type, and my run type is using a TPU. I think it is interesting to see. I could try a GPU and see if that's faster, but I think on most tasks like this, a TPU is going to be better. In your code. That is a great question. I do know that the Keras code is relatively optimized to use it. But no, that's a fair point. Maybe I'm not actually taking advantage of it. If you think that is an issue that I'm facing, maybe I need to go and check that again. My understanding is that Keras should be pretty good about specifically taking advantage of it in the environment. I know if you're running on your local machine, which is actually one of the reasons I'm not doing that, is it's like a really big hassle to actually get your code to use hardware acceleration. But no, I thank you for the feedback. I will double check to see if I could be doing this faster. But I'll look at that. We're cranking through. And yeah, maybe this could all be faster. I don't know. I will do some more research. And okay, cool. So now let's plot our loss and accuracy. And okay, this is great, right? So our loss is looking good on both training and validation. And you see that our training loss does decrease faster than our validation loss. But they both are going down the entire time, right? And remember, the one thing that we changed is we just threw a bunch of data at it, right? We could also look at accuracy, if I can spell accuracy correctly. Accuracy, is that right? We can also look at validation accuracy. And we see a pretty similar story, right? Where it's like, okay, our training accuracy does get up a little bit faster, but our validation accuracy is basically going up the entire time. Now, I'll reiterate this, is okay, our training accuracy is like 78%, our validation accuracy is like 76.9%. This is actually not wildly better than we got with our logistic regression model yesterday. In fact, depending on how you think about it, it might actually be worse. I would say our logistic regression model was only being tested on, I think, like 1,000 records or something, and this is being tested on like 100,000 records. And so broadly, I'm just more confident in this accuracy. But it is this question of, okay, do we really trust the accuracy we were getting yesterday? We weren't using validation test sets. We were just running on our tests, or we were using validation sets. We were using just our test set. But now I think the final thing that we'll try to do, I know we're technically at time and somebody else might be trying to get on stream. I should probably check the schedule. But we will try to evaluate on that test set that we held out at the very beginning. And so we will just run our model. And we should be able to say model evaluate, if I recall correctly. And we will just pass in, instead of x train and y train, we will finally actually use x test and y test encoded. And this should run relatively fast. And this is now data that this model has never seen ever, not even on a quiz. And this, if you are a machine learning engineer, this is exactly what you want to see, that when you finally pull out your test data set, you actually do better than you were doing with your validation set, right? That means that you are not overfitting and you can have really, really good confidence that this will replicate, right? And so, okay, we can predict it 77% of the time. Maybe that is actually some kind of theoretical limit, right? I mean, you could think about how humans would do this task, and you probably would not have humans getting it right every time, right? A human doing this task, they might only get the specific 5-star number. They might only get it right 2/3 of the time, right? And so if that's the case, then we're getting better accuracy than that. Okay, so we are technically now 1 minute over time. But I really, really want to say thank you so much for being here. I'll do a really quick recap. So we went through basics of Python. We learned basics of NLP and rule-based models by looking at tokenization and lemmatization and the corpora and tokens and documents. And then yesterday, we dove into machine learning, where we automatically generated our weights and we automatically generated our list of good and bad words from the data set. And then we took a look at scikit-learn and used pre-made models. But in order to use those pre-made models, we had to learn how to vectorize our text. Today, we jumped up to really modern machine learning using Keras and Tensorflow, and we used a convolutional neural network. This is a fun phrase you can throw out, is that I know how to use convolutional neural networks to get a sense of words in context and have our model understand that one word can affect the word after it. And we took a deep look at overfitting and how to correct it. We looked at using more data and dropout and using validation test sets. So we covered so much this week, and I am so incredibly grateful that you all stuck with me. It is one of my favorite things to nerd out about. I learned several things, and there's one thing that I'm going to go and check to see if I'm using hardware acceleration correctly. But I really, really appreciate y'all sticking with it with me. Y'all have been a blast, and I really appreciate y'all working with each other to answer questions and to drop links and everything. Yeah, I guess thank you so much. Happy Global Hack Week. I will drop the form one more time if you have any other feedback on what you want to see in the future. I would love it if you told me what you want to cover in the world of machine learning at the next Global Hack Week, because that will be a blast. Thank you so much for your positive words of feedback. And I think if we're okay with it, I'll just play us out on Kalimba, and we'll call it a day. Does that sound good? All right, we'll say it sounds good. All right, let's line it up. There we go. All right, thank you, friends. Happy Wednesday. Happy Global Hack Week. And I will see y'all around. Take care. Bye.